Issues of exponential growth will always bring up story problems, and story problems, if you want to solve them, and exponential problems, you're going to have to use a log. So up here I have a toolbox for different equations that you're going to need, so you don't have to memorize them. So your homework is to do this paper, so I'll just kind of give you a hint on some of them that I think are going to hang you up, and it should be a pretty short day today. So just to give you a start here, a town has a population of 1,000, is growing by 5% every year. Anytime we talk about exponential growth with no compounded interest or continuous compounding or anything like that, it's just going to be your regular y equals ab to the x formula. Nothing fancy there. So I'll start you out on this one. So a is how many you start with. You have 1,000. Just a quick reminder, if you want to grow by 5%, that is not 0.05. That makes things smaller. We got to grow, so we got to slap a 1 in there. And then if we want to have it for 7 years, you're going to go power 7. Your calculator will handle the PEMDAS just fine. Type that in and you'll be fine. How long? As soon as you see the question, how long, what you could do is just cross out the n. When you see how long, cross out the n, a log. Okay, that's how do you do it? With a log. So as soon as you see the question, how long, you're going to use the logarithm when it comes to exponential growth problems. The population doubles. So if we start with 1,000, you're going to end up with 2,000. Our growth rate's the same, and we have 1.05 to the power of x. X because we don't know how long it's going to take. Now we have to log, and remember what we have to do. You can only log the thing that has the power. You can't log the whole problem. So our first step is to divide by 1,000. So if I do that, if I divide by 1,000, I should have 2 equals 1.05 to the x. We're going to log both sides, log here and log here. And when you do that, you get log 2 is going to be equal to x log 1.05. And you can divide now and be done. I'll let you handle that. I'll also let you answer the next one. Let's see. Number 2 is very similar, except for now. The only difference is going to be we're going to use the compounded formula. So put that in there, put in the time, how long to a double, same idea. Just be careful that when you log both the n and the t, both these numbers are going to come down in front. So it will be similar to the one we just did, but just a hair differently. Continuously. Let's see. Continuously means we're going to use the PERT formula. How long till it doubles? So if we start with 4,000, right over here, start with 4,000, we're going to have $8,000 equal to 4,000 e to the 0.04 t. Divide again, so you're going to have 2 equals e to the 0.04 t. The only thing I want to give you a heads up on here is any problem with e, there's going to be one specific log that's going to be a little handier. It's going to be the natural log. Anything with e, now instead of using the common, we're going to natural log both sides. When you do that, these just cancel, and you'll have natural log 2, and then divide by 0.04. Make sure you close natural log 2 closed. All right. Let's see. This next one, I'm not going to tell you exactly how to do it, but if investments are losing 7%, you have your starting amount. The only thing I'll tell you is that your growth factor on this is not 0.07, and it's also not negative 0.07. You have to take your investment and make it lose 7%. So it starts out with 100%. Losing 7% would help you figure out what your growth factor is. All right. Hardest one is on the back. I did a little digging and just about some facts about coronavirus, because really the coronavirus it's growing exponentially, and that's what this log is good for. So I mean, kind of timely for what we're learning. So a resource I recently read said that someone who does not social distance will infect 4 people every 5 days with coronavirus. So let's think about that. The equation we're going to use is just y equals ab to the x. And let's just figure out, if no one exercised social distancing, how many people would be infected in 30 days. Assuming we start with that one person in Wuhan, we're going to go 1. And if you're infecting 4 people, that's multiplying by 4. You're going to go 4 more, 4 more, 4 more. So I'm going to go times 4. and then power x. But now we just have to think, here's the tricky part. I don't want to just plug a 30, because that would say start with one person and go times 4 30 times. Because it doesn't say that we're gonna that we infect 4 people every day. It's only every 5 days. So how would I take my days and divide them up into 5-day chunks? Well, the way that you do that is you take your exponent and you divide by 5. Now when I plug 30, it will be divided into 5-day periods, so your exponent is going to be 6. So 1 times 4, and then we're going to go power 6. 4 power 6 is going to be 4,096 people, just from not from social distancing. So now we have the next question. How long? We'll take this very same equation, a b to the x, and we to infect 1 billion people. That's what we want to know. So we have 1 billion. It's going to be equal to 1 times 4 to the power of x over 5. Well, usually you have to divide this first number away, but right now it's, times 1 does nothing, so we can just kind of get rid of it. You can go right to the log. When you log it, you're going to have log a billion it's going to be equal to x over 5 log 4. Okay, these are multiplied, so you can divide by log 4 and divide by log 4, and then go times 5. Okay, so divide by log 4 on both sides and go times 5, and you'll have your answer. I want you guys to do as much as possible. Down here, if we do, you can make it grow only half as fast. So instead of the 4, we can put a 2 in there. Down here, I thought this is interesting. I think Alex will like this for sure. Real diseases cannot grow exponentially. We run out of people to infect. We run out of people in an area to infect. So what happens is you'll see something that goes like this. You'll see something that grows exponentially and then planes off, and that's what every disease or anything like that has to do. So here's a little bit more accurate model for what's going on. It's similar to what's going on here, but just a little bit more accurate. If you have time, fiddle with it. If you don't, that's okay too.